Assalamu alaikum wa rahmatullahi wa barakatuh. This is Dr. Ali El-Moursy again, and we are actually at lecture number 1903, the third part and the last part for the decoders lecture 1903 in DLD, in Digital Logic Design. The last thing that we need to discuss is how can I use the decoder circuit to implement other functions. We learned in the first chapters, chapter 2, chapter 3, how can I use the different logic gates in order to implement the different functions. Assume that I don't have logic gates. Assume that I have a decoder. Okay? Can the decoder help me to implement the functions? The answer is yes. And this is actually what we want to learn in this last part. Okay? Okay, decoder usages. How can the decoder, okay, or use the decoder to implement functions? Any function. Can the decoder help me in doing that? So let's go into the example. Okay, example. Implement the following function using decoders and any extra needed logic gates. The function f is given to me as f equals to the sum of 0, 2, 4, and whatever, 6, whatever, or let's say 5, anything. Can I implement the function f using the decoder? Why yes or no, and why yes? There is some property of the decoder that we may not pay attention to while we are designing the decoder. The decoder as a circuit is actually giving me all the min terms between the inputs. So if I have 3 input function, okay, or if I have the decoder is actually have 3 inputs, it will have 8 outputs. Those 8 outputs representing what? Representing the different min terms between the inputs. By definition, D0 matches M0, D1 match M1, D2 match M2, and so on. So that means it's piece of cake. Okay, I can use the decoder to implement any function, because actually if I'm using the inputs of the function match the inputs of the decoder, this automatically means the outputs of the decoder will be the min terms between the inputs. I know that f of x, y, and z, if it equals to the summation of 0, 2, 4, and 5, that means the function can be written as m0 or m2 or m4 or m5. And if I'm using the inputs of the decoder equals to the x, y, and z in order, that means, this means M0 in the decoder is D0, M1 is, M2 is D2, M4 is D4, and M5 is D5. So what is missing in the decoder in order to implement the function? So first of all, I have to use appropriate size decoder. What does it mean by appropriate size? If the function is 3 inputs, I have to use 3 by 8 decoder. This is step number 1. Step number 2, I have to connect the inputs of the decoder to the inputs of the function in order. Who is X? X representing the most significant input. What is the most significant input here? It is I2. So X should be connected to the input 2, Y should be connected to the input 1, and Z should be connected to the input 0. Automatically the decoder here will give me all the 8 min terms, M from 0 till M7, between X, Y, and Z. Now my function has only min terms M0, M2, M4, and M5. And in order to get F, all what I have to do is an ORing between those. So these are actually the outputs of the decoder is the min terms of X, Y, and Z. So if I use an OR gate, and this OR gate is actually connected to D0, connected to D2, connected to D4, and D5, the output here will be simply the function F. So basically, okay, that is just a okay. So basically, okay, I can, by the help of appropriately sized decoder and an OR gate, I can implement any function of 3 variables. What if you give me, let's take another example. You give me another function G or S, function of X, Y equals to X or maybe Y. Can I implement this function using decoder? The answer is yes. But first I have to put the function in SOM. I want to know where is the min terms for that function. So you can here use any method, okay, that we have learned, either from chapter 2 or for chapter 3. Okay, I can build a schema for this to identify the min terms, or I can use expansion or whatever. Okay, so this function is simply, if I use the Boolean algebra expansion or using K-map, this is actually X, Y bar, X, Y, X bar Y, X, Y. This is, I'm using expansion. So the function is actually X, Y bar or X, Y or X bar Y. So that means the function S is the summation for the min terms, 1, 2, and 3. So that means I can implement the function S using first appropriate size decoder. What's the size decoder or decoder that you use here? This function is 2 inputs, so I will use 2 by 4 decoder. This 2 by 4 decoder has 2 inputs. The inputs will have the numbers 0, or let us follow the same standard, or the standard that we use, 0 and 1. And this 2 by 4 decoder has how many outputs? It has 4 outputs. 0, 1, 2, 3. Okay? So accordingly, if I'm connecting X, which is the most significant input, X here and Y here, I will get the 4 min terms. This function S has ones at which min terms? At 1, 2, and 3. So if I am using an OR gate connecting 1 and 2 and 3 together, the output from the decoder here will be my output S. Agree? Make sense? So this is a very useful application for the decoders. I can use the decoder to implement with one decoder and one OR gate. I can implement multiple functions. Okay? A very useful example here, or very interesting example that we usually give, is how can I use the decoder to implement half adder. Can you see this? Okay, so I will erase the board now. Now let's take another example, very well known common example that we give. Okay, implement, or let me put the wording of the problem. This is actually, I think, exists in the homework. Okay, use decoder to implement half adder. You still remember the half adder? Yes, half adder is a circuit. You still remember it? That has two inputs, A and B, and two outputs, S and C out. Half adder. Okay? So it has two outputs and has two inputs. Do you still remember the TT for the half adder? Yes, the TT for the half adder tells me that I have here A, B, C, S, and C out. How many rows? The half adder adds the A and B together. So adding A and B together, 0, 0, 1, 0, 1, 0, 0, 1. Okay, so that means I can write S as A and B equals to the sum of the mean terms 0, 1, 2, 3 designators. So it's the sum of 1 and 2. And the C out, A and B, is the sum of just 3. So in order to implement this using the decoder, what is the size of the decoder? I have here two inputs, so I have to use 2 by 4 decoder. And this 2 by 4 decoder, I will have 0, 1, 1, 2, 3, 4, 0, 0, 0, 1, 2, 3. Okay, so the most significant here in that case, I label it as A. A here and B here. Now, for S, how can I get S out of this decoder? I have to OR between the mean terms 1 and 2 to give me the output S. Now what about C out? C out is simply this. So what we have drawn here is an implementation for the all of this circuit that we have just implemented right now is the circuit for the half adder, but inside the circuit we do not use the XOR, we do not use the logic gates, we used a decoder. Okay, any function I can implement. Okay, I have to use appropriate size decoder, I have to use enough of OR gates, and I can implement any function I would like. Okay, so this is the end of the decoder lecture, and inshallah in lecture number 20 we will design, or we will use, or we will build, or we will learn something new called the multiplexers. Thank you.